All right, I think we can start. Welcome everyone to the review session for Math 21 LE3. So I'll just start my broadcast here, and then we can start working on the samplex. All right, so for the first problem, um, we're basically tasked with evaluating this limit. So the limit as x approaches 0 of x squared sine 2x over 1 minus cos 2x. So just as a review, your hyperbolic cosine is equal to e raised to x plus e raised to negative x over 2. And your hyperbolic sine is equal to e raised to x minus e raised to negative x over 2. So what we can do here is first check for indeterminacy. So when we plug in x equals 0, the top side goes to 0, and then the bottom side here, it also goes to 0, because um hyperbolic cosine of uh 2 is essentially like e raised to 2 plus e raised to negative 2 over 2. So that basically results in the denominator being equal to 0. So since it's a indeterminacy of the form 0 over 0, what you can do is apply L'Hopital's rule. So what we'll do here is we'll take the derivative of the numerator and also the denominator. So for the numerator, what we'll get is x squared cosine 2x times 2 plus 2x sine 2x. So that just follows from product rule and chain rule. And then the bottom side becomes 1 minus 2 sinh 2x, because the derivative of hyperbolic cosine is just hyperbolic sine. So if you'll plug in x equals 0, you'll notice that it's also indeterminate. So this is once again 0 over 0. So we essentially have to apply L'Hopital's rule again. So the numerator becomes negative 4x cosine 2x plus 4x cosine 2x plus 4x cosine 2x plus 2 sine 2x. So that's the numerator. And then the bottom becomes negative 4 hyperbolic cosine 2x. So that's just from the chain rule. So essentially, the derivative of sinh is cosh, and the derivative of cosh is sinh. So when you plug in x equals 0, this term cancels out, this term cancels out, this term, and this term cancels out. So you're left with this term here. So it's going to be negative 4 over negative 4 times cosh of 0. And that's going to be equal to 0. So that's your final answer. So for the second problem, we're given this one. Limit as x approaches 1 from the right, 3x minus 2 raised to coth x minus 1. So your coth here is gonna be coth over sinh, which is equal to e raised to x plus e raised to negative x over e raised to x minus e raised to negative x. So what you'll end up getting when you plug in x equals 1 is you'll essentially get e raised to 1 plus e raised to negative 1 over e raised to 1 minus e raised to negative 1. But since it's coth of x minus 1, what ends up happening is that this goes to infinity. So the top side will be e raised to 0 plus e raised to -0. So essentially, like, you can check that as it approaches the right side, this will become positive infinity. So essentially, we're given an indeterminate form because this one goes to 1, but this one goes to positive infinity. So your indeterminacy here is 1 raised to positive infinity. So what we should do here when you're given this form is you should try to make use of natural logarithms. So writing the original limit here, 3x minus 2 cos x minus 1. This is equal to limit of x approaches this one of e raised to cos x minus 1 ln 3x minus 2. So what we need to do is essentially find the limit of this one. So just rewriting this, you got limit of cos minus 1 ln 3x minus 2. So this is going to be essentially like positive infinity, and this is going to be 0. So this is again indeterminate of the form infinity times 0. So when you're faced with this, you should always try to rewrite it in the form that fits either 0 over 0 or infinity over infinity. So you can apply L'Hopital's. So what we can do here is rewrite this limit as follows. So cos is just 1 over tanh. So that's going to be ln of 3x minus 2 over hyperbolic tangent of x minus 1. And then it's easy to check that this is going to be indeterminate of form 0 over 0. So what we can do here is use L'Hopital's to get the derivatives. So the top side is going to be 3 over 3x minus 2. And then the derivative of hyperbolic tan is secant squared, hyperbolic secant squared x minus 1. And then this is going to be equal 3. So this is the limit of the original exponent here. So this goes to 3. And so your original limit is e raised to 3. All right. So the next problem here, we're tasked with finding the x coordinates of the absolute extremum points of f of x equals sine squared x minus cosine x on the interval -3 pi over 4 inclusive until pi over 4 exclusive. So first things first, what we can do here is take the derivative of the function to get 2 sine x times cosine x plus sine x. And then you can factor out the sine terms to get sine x times 2 cosine x plus 1. And then you want to set this equal to 0. So you have two cases here. So sine x equals 0 or cosine x equals -1/2 because of this one. So it's easy to check that sine x equals 0 whenever x equals pi k, where k is an integer. And then for cosine x, it's -1/2 when x is, if I'm not mistaken, 2 pi k over 3. So that corresponds to 120 degrees and 240 degrees, which correspond to -1/2. But we're given this interval, -3 pi over 4 until pi over 4. So we need to check, first of all, like when we can satisfy these things. So for sine x equals 0, it's easy to check that the only value that satisfies it is x equals 0 on the interval. And then for cosine, it's -1/2 when x equals -2 pi over 3. So that's when k equals -1 here. So that's those are basically our critical values. But then the problem is here we're given, sorry, this is non-exclusive pala. So this is should be a parenthesis. The problem here is we're given an original bound. So we have to check also, in addition to x equals 0 and x equals -2 pi over 3, we also have to check x equals -3 pi over 4 and check the limit as x approaches the pi over 4 from the left-hand side. So first of all, let's check this one, x equals 0. So this gives us f of 0 equals sine squared of 0 minus cosine of 0 equals -1. Then for the other critical value here, it's -2 pi over 3. Sine squared -2 pi over 3 minus cosine -2 pi over 3. So that's going to give us square root of 3 over 2 squared minus -1/2. So that's going to give us 3 over 4 plus 1/2, which is 5 over 4. Then let's also check f of -3 pi over 4. That's going to be 1/2 plus square root of 2 over 2. By the way, it's 1/2 because we square it's essentially square root of, sorry, it's square root of 2 over 2 squared plus square root of 2 over 2. So that's going to give us 1/2 plus square root of 2 over 2, which is 1 plus root 2. Then finally, we also have to check the limit as x approaches pi over 4 from the left-hand side. So to get that, of the original function here, sine squared x minus cosine. It's easy to plug this in because everything is continuous. There's nothing weird going on. So it's gonna be square root of 2 over 2 squared minus square root of 2 over 2 equals 1 minus root 2 over 2. So looking at all of the values here, the largest value is at -2 pi over 3, which is 5 over 4. So absolute maximum, and then 5 over 4. Then your absolute minimum, looking at the values here, you get the absolute minimum is at x equals 0 for -1. Right. So that's our answer for this problem. So let's move on to problem 3. So a particle is moving along a horizontal line. Its position on the line in t seconds is given by 2t cubed minus 21t squared plus 72t minus 15, where s is in feet and time t greater than or equal to zeros in seconds. Then we're given a table of signs for velocity and acceleration. So first, let's determine the time intervals when the velocity of the particle is decreasing. So for this one, it's easy to check that the velocity of the particle is decreasing whenever its derivative, which is acceleration, is negative. So looking here, acceleration is negative at three intervals. You have 0, 3, you have 3, and you have 3, 7/2. So essentially, the interval on which um acceleration is negative and therefore velocity is decreasing is 0 until 7/2. Then next we need to check when velocity is constant. So here it's really easy. Simply check when its derivative is equal to 0. So acceleration is equal to 0 at t equals 7/2. So that's your answer for number 2. And then here, um, we're asked from the third to the ninth second, when is the particle at its leftmost position? So we're considering the third to the ninth second here. So if you notice, from from 3 until 4, the derivative is negative. So it's still decreasing. So the particle is still moving to the left. So we haven't reached our minimum yet. But then you notice at t equals 4, Vt equals 0. So we've hit our absolute minimum, or at least local minimum here. And then notice that for t greater than 4, so particle moves to the right. So essentially, like what happens here is that the particle goes to the left and then stops and then continues to go to the right. So it ends up hitting its leftmost position at t equals 4. Next, we need to find out where is the particle located when it attains its absolute minimum velocity. So simple here, by the same logic, um, we look at the derivative of velocities. So that's your acceleration. So you can notice that from 0 to 7/2, acceleration is negative. So velocity is still decreasing. And then from at 7/2, a equals 0. And then from 7/2 until from 7/2 until positive infinity, acceleration is greater than 0. So v attains its minimum at t equals 7/2. So your v would look something like this. So it keeps decreasing until it hits 7/2. Then this is when your acceleration is 0. So we just need to find um the position of our particle at this point. So that's really simple to get. All you need is to get s of 7/2, which is going to be 2 times 7/2 cubed minus 21 times 7/2 squared plus 72 times 7/2 minus 15. So that's going to be 343/4 because that's 2/8 minus 49 21 times 49 over 4. Sorry. Plus here, that's 36 times 7, so that's 252 minus 15. And then you can simplify everything. Comes out to 131 over 2. So that's your final answer here. Finally, for number 5, what is the total distance traveled by the particle after 10 seconds? So I guess a mistake you guys might make here is you can't simply integrate S of t. I don't think you guys have done integration yet, but this is like wrong because the magnitude, you're taking the absolute value of the distance traveled. So you don't care about the direction here. So what you need to do for this is to identify your critical points. So your critical points would be points in which your velocity is 0. So t equals 3 and t equals 4. And then you also need to consider the endpoints, which are t equals 0 and t equals 10. So for s of 0, it's going to be negative 15. And then for s of 3, going to be 66. For s of 4, it's going to be 65. That's your position. And for s of 10, it's going to be 605. And so your distance traveled, um, going from here, you're essentially like increasing, and then you're decreasing, and then you're increasing again. That's the reason why that's the reason why we had to check critical points, because you need to make sure that basically the journey from negative 15 to 66 is going in one direction only. And then same for all of the other intervals. So from 0 to 3, you travel a distance of 66 minus negative 15, so that's 81. And then from 3 to 4, you travel a distance of 1. And then from 4 to 10, you travel a distance of 540. So your total distance traveled is 622. All right, so that's our answer for this. Now suppose another object is on the same horizontal axis with a position function r of t equals 2t cubed minus 17t squared plus 93t minus 10. And then we need to find out if the two objects here will collide. So to check whether or not the two objects will collide, we need to equate this to s of t. So at any time, let's say r of t equals s of t, that means the two objects will collide. Collision if r of t equals s of t. So then equating this to s of t, we get 2t cubed minus 21t squared plus 72t minus 15. And then if we find the value of t that satisfies this, we collide. Otherwise, we're not going to collide. So just collecting the terms here, we'll get 4t squared plus 93 minus 72 is 21t. Then negative 10 plus 15 is 5. And that's pretty easy to factor this. You essentially get, but sorry, 0 equals, or t squared plus 21t plus 5. You can factor it as follows. 4t plus 1 times t plus 5 equals 0. So from here, you get negative 1/4 and negative 5, which are all less than 0. So the objects do not collide. All right. Now let's move on to part 4, which is local linear approximation. So approximate e raised to negative 0.02 times hyperbolic sine 0.01 using local linear approximation of at x equals 0. Just write this one. So I guess that's a rationale for your local linear approximation as a refresher here. So your local linear approximation is simply equal to your function at that point plus the derivative of that function times x minus x naught. And this is valid for all x that are close to x naught. So we're given x naught is equal to 0, but we first need to identify f of x. So a really big hint here is to use this 0.01 value since it's very small and it's very close to 0. So a nice way we can define the function here is simply by creating is simply by setting f of x equal to e raised to negative 2x times hyperbolic sine of x. So we're essentially approximating f of 0.01. So to do this, we first need to take the derivative to get this part here. So taking the derivative of f of x, we get negative 2 raised to negative 2e raised to negative 2x times hyperbolic sine of x plus e raised to negative 2x times cosh of x here. And then checking to get and then our local linear approximation here is going to be f of 0.01 is roughly equal to the approximation L of 0.01, which is going to be equal to f of 0 plus f prime of 0, sorry, times 0.01 minus 0. So f of 0 here, it's easy to check that this is equal to 0 because of the sinh term. So that's 0. And then f prime of 0 is 1 because of cosh. And then you're multiplying this by 0.01 minus 0. Get 0 plus 1 times 0.01 equals 0.01. So that's your local linear approximation at x equals 0. All right, so let's solve this next problem. So we're moving on to part 5 now. A glass door has an aluminum outer frame that is 3.5 cm wide on the left and right side, 5 cm wide on top and bottom. If the glass area is 630 centimeters squared, what should be the dimensions of the glass area to minimize the total area of the door? So when you're faced with problems like this, it's always helpful to draw a diagram. So essentially you have your frame here, and then you have some sort of door. We're given that it's 3.5 cm, 3.5 here. And then this one is 5 cm and 5 cm. And then let's also set some variables. So let this be the length and let this be the width, right? We're also given that the glass area, 630, is equal to length times width, because that's the area of this shape here. So from there, you can isolate one of the variables. Essentially, let's just write W is equal to 630 over L, which will be helpful later on. We need to minimize the total area of this shape here, which is going to be equal to L plus 10 times W plus 7. Actually, it's probably better if you just switch the variables. So L is equal to 630 over W. So what you'll get is you'll minimize 630 over W plus 10 times W plus 7. So that's equal to 630 plus 4410 over W plus 10 W plus 70. So that's equal to 10W plus 4410 over W plus 700. And then your constraints here, your W is it's essentially unbounded. You can essentially set it to anywhere between 0 and positive infinity. So no constraints here. So what you need is to find the absolute maximum for this. So taking let's just set this equal to f of x. So taking the derivative of that, you get 10 minus 4410 over W squared. So that's equal to 10W squared minus 4410 over W squared. And then you want to set this equal to 0. So you can isolate the numerator to get W squared minus 441 is equal to 0. Sorry. So W equals 441. Or W is equal to plus minus 21. But we obviously take W equals 21 here. So this is our critical number here. And so, but we don't know yet whether or not this is our absolute maximum or absolute minimum. So what we need to do from here is to take the second derivative. So f double prime of x is equal to 8820 over W cubed. So plugging in 21, this is gonna be sorry, f prime of W. So f double prime of 21 is greater than 0. So what this tells us is that 21 is an absolute minimum. So this is what we want. So from here, we got W equals 21, and then L is equal to 630 over W equals 630 over 21 is 30 cm. So these are our answers. Okay, nice. So for the next problem, a new smartphone called Ophone will be released this month. The price demand function and the cost in pesos of producing the said smartphone is given by P of x equals negative 450 over negative 450 minus x over 6. And capital C of x is equal to 800 plus x squared over 2 minus 2000 x. So it's important to note that P of x is unit price, or sorry, it's unit price, while capital C of x is total. So we are estimating with marginals. So we are tasked with determining the profit earned in selling the 101st unit. So to do this, essentially what we need to get is the profit function. So the profit function, capital P of x, is equal to the revenues minus the cost here. So it's going to be x times P of x minus capital C of x. So this is your units times revenue per unit, and this is your total cost. So what you get is your P of X, capital P of X, is equal to, so just multiplying x to small p, you got negative 450x minus x squared over 6. Then subtracting c of x, you get minus 800 minus x squared over 2 plus 2000x. So simplifying, what you'll get, just a bit of algebra, is negative 4x squared plus 9300x minus 400 over 6. So to get to basically use the marginal difference here, we're gonna have to differentiate the profit function. So p prime of x is equal to negative 8x plus 9300 over 6. And just simplifying like terms here, that's negative 4x plus 4650 over 3. And then we're basically going to use this approximation to approximate the differential gain. So it's not just P of 101. You also need to subtract the current state, which is 100. So this is your differential profit, which you're going to set roughly equal to P prime of the starting point, which is 100. So plugging it in here, you'll get negative 400 plus 4650 over 3. So this comes out to 4,200 over 3 pesos. So this is your approximation. Next, we're tasked with finding the production level that will result in the least average cost per unit. So earlier, C of X was the total cost. So to get the average cost per unit, you simply divide by X. So that's gonna give you 800 over X plus X over 2 minus 2000. And let's set this equal to a function called g of X. So what we can do here is find the minimum, which is first we have to differentiate. So this would be negative 800 over x squared plus 1/2. So collecting everything, you get negative 1600 plus x squared over 2x squared. And then we need this equal to 0. So x squared equals 1600, or x equals plus minus 40. So taking the positive value here, because you can't have negative number of units, you take x equals 40. And then again, we need to check whether or not this is an absolute maximum or absolute minimum. So we check the second derivative. Sorry, this is g. So g double prime of x is equal to 1600 over x cubed. So you get that just by differentiating, this again. So it's easy to see na g double prime of 40 is greater than 0. So it means that x equals 40 is an absolute minimum, right? Okay, so this is our final answer. Next, let's move on to problem 3. The Marines are 55 miles south of Wano Kingdom, sailing towards it at a speed of 12 miles per hour, when the Straw Hat Pirates start sailing from Wano due east at a speed of 6 miles per hour. How fast is the distance between the Marines and the Straw Hat Pirates changing after 4 hours? And we have to indicate whether the distance is increasing or decreasing. All right, so given problems like this, it's always helpful once again to draw a diagram. So you essentially have Wano here. So this is at t equals 0. You have your Wano. So this is at t equals 0. And then the Marines are 55 miles south. And then the Straw Hat Pirates are also here. So Wano and the Straw Hat Pirates are at the origin here, and then Marines are south, right? And then after 4 hours, t equals 4, what ends up happening here is that Wano is over here. The Straw Hats are sailing due east. So these are the Straw Hats. And then the Marines are somewhere further up north because they've been moving up, and then Straw Hats are moving to the right. For these Marines here. And then this is essentially the distance between them. Let's call it Z. Let's call this Y. Let's call this X. Right. So essentially what we need to find out is after t equals 4, we need to determine dz over dt. So what we need to do is essentially establish a relationship between x, y, and z. And so there's a really simple relationship we could use. It's the Pythagorean theorem here. So we're given a right triangle. So essentially what we have is x squared plus y squared equals z squared. And let's just shift everything here. So z squared equals x squared plus y squared. And then we need dz over dt. So what we should do here is we can differentiate everything with respect to time. So it's just the chain rule. So first differentiate z with respect to itself. That's 2z multiplied by dz over dt. And then we're given 2x dx over dt plus 2y dy over dt. So this is the relationship that holds at any point in time. To make things easier, let's just cancel out like terms here. Z dx over dt plus y dy over dt, right? So what's left now is we have to find out z. We have to find out x dx over dt, y dy over dt. And we can actually get it from the original diagram. So we're given that dx over dt, first of all, is equal to whatever the speed the Straw Hat Pirates are going at. So the Straw Hat Pirates are sailing east, due east at the speed of 6 mph. So dx over dt is 6. dy over dt. So dy over dt is decreasing because so this length is actually decreasing as the Marines go up. And so we should use a negative value. So dy over dt is equal to negative 12. And then for the x value, at t equals 4, the at t equals 4, the Straw Hat Pirates have sailed 6 times 4, so that's 24 miles. Then for y, this length here, so z is equal to 25. So from here, we essentially have like everything we need. So we just have to plug values in. So 25 times dz over dt equals 24 times 6 plus 7 times negative 12. So that's going to be 60 over 25, just 144 minus 84. So that's 60. And then that's going to be equal to 12 over 5. So this is in miles per hour, and since it's a positive value, increasing. So that's our final answer. All right, so we're done with the problem solving part for the most part. Next part here is a bit tricky. It's true or false. So right true if the statement is always true, and false if otherwise. Number one, a continuous function f of x attains its absolute maximum at exactly one value of x. So this one is false, and there's actually like a very simple counterexample, plenty of counterexample here. You can basically take sine of x or cosine of x. So if you look here, that continues to oscillate. So your absolute maximum is always here. So the essentially your value is not unique. So number one is false. Number two, revenue and profit functions are always non-negative. So this is false once again. Because profit can be negative. If cost. So if costs are higher. Yeah. Number three, let f and g be differentiable functions in an open interval I containing a, except possibly at a, and g prime of x is not equal to 0 for all x in I except a. Then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x over g of x, provided that the limit exists or is infinite. Okay, so essentially, like it's a bit of tricky notation here, but what it's asking is, can we essentially apply L'Hopital's rule anytime? So what it's basically asking us is, can we always apply L'Hopital's rule? And the answer to this is false, so no. So L'Hopital's rule only applies to indeterminate forms of infinity over infinity and 0 over 0. So we can't apply that theorem. And I guess just as a simple counterexample here, let's take two functions. F of x equals, let's say, x. And then, sorry, it should be g of x. And then g of x, let's set it to, let's say, x plus 1. And then for our a, let's set a equals 0. So both of these are differentiable functions on R. So these are differentiable on R. So essentially, like we just need to show that this breaks the rule, right? So we need to check if the limit as x approaches a of f of x over g of x, so that's the limit as x approaches 0, is equal to the limit as x approaches 0 of their derivatives, right? So for x, it's going to be 1, and then for x plus 1, it's also going to be 1. So it's easy to check that 0 is not equal to 1. So contradiction here. So it's false. So we found a counterexample to this statement. All right. So for the next one, number 4, suppose f prime of x times g prime of x is not equal to 0 when x is within 3 and 6 except for 5. then g prime attains its absolute minimum at x equals 5 on the interval. So it's somewhat tricky here, but what we need to check essentially is whether g prime attains its absolute minimum at x equals 5. So we know that g prime of 5, so x equals 5 is a critical point here. But then what we notice here is that g double prime of 5 is equal to -2. So this is less than 0, right? So one way to think about it is simply to set, let's say, an arbitrary function, let's say h of x, you set it to g prime of x. So h of 5 is equal to 0, but the derivative here, h prime of 5, is less than 0. So what this tells you is that 5 is an absolute max. So, or at least it's a maximum. It's a local maximum here. So, local maximum. So, g prime does not attain it at x equals 5. So, the answer to this is false. So, for the next problem, using local linear approximation, the approximate value for g prime of 4.99 is 0.02. So what we need to do here is, first of all, define our function. So 4.99, what you can do here is you can set x sub naught is equal to 5. Or actually, there are several ways you could do this local linear approximation. I can present both. So for now, let's set x sub naught is equal to 5, right? And then for simplicity, let's also do h of x is equal to g prime of x. And we need to approximate uh, h of 4.99, which is also equal to g prime of 4.99, right? So h of 4.99 is going to be roughly equal to the local linear approximation at 4.99, which is going to be, so given our x sub naught is equal to 5 here, it's going to be equal to h of 5 plus h prime of 5 times 4.99 minus 5. So, and then substituting back, what we get here is this g prime of 5 plus g double prime of 5 times negative 0.01. So what we get here is you can substitute this. So this is equal to 0 from the problem statement. This is equal to -2 and then times negative 0.01. So this is 0.02. So this is true. Yep. And then if you so this is when we set x sub 0 is equal to 5, but then you can also set it equal to, let's say, 0. There's a clean way to do it. If instead we'll just have to redefine our function a bit, but we'll arrive at the same answer. So what we can do here is redefine our function. Instead of h of x equals g prime of x, we'll use h of x is equal to g prime 5 minus x. Then instead of approximating h of 4.99, we approximate the h value of 0.01 is equal to g prime of 4.99. So we can use this local linear approximation here. It's very close to 0. So with x sub naught is equal to 0. So this is going to be equal to h of 0 plus h prime of 0 times 0.01 minus 0. So that's just 0.01. So your h of 0 here is just g prime of 5, which is 0. And then your h prime, this is where it gets tricky. So it's not equal to g prime of x. So what you have to do here is differentiate. So that's going to be equal to negative g double prime 5 minus x, just from chain rule. So what you get here is that h prime of 0 is equal to negative g double prime of 5, which is going to be equal to negative times negative 2, which is equal to 2, right? So plugging this back in here, so what you get is that 0, so you essentially get 0 plus 2 times 0.01. So what you'll end up with is 0.02. So it's true once again. So essentially, like there's several ways you could go about local linear approximation. So you could either use x equals 0. You could also use x sub naught is equal to 5, and actually like several other ways you could do this as well. So there are really a couple of ways you could do local linear approximation. So we've gone through the first samplex, and so I think next we could do another one if time permits. So we still have around 45 minutes here, so we can go do another one. All right. So this is the second samplex now. It should be roughly the same here. So number one, find the absolute extrema of the function f of x is equal to x cubed plus 5x squared plus 8x minus 10 on the interval -2, -1 inclusive. All right, so it's a polynomial here. So just as an initial check, it's continuous on R. So f of x is continuous on R, right? So pretty simple way to do it is to check the first derivative. But before we do that, when you're given a bound, so what we should do is check critical numbers on the interval, but we should also check the boundaries. So these are the two things we have to do to identify like the absolute and the absolute maximum and minimum here. All right, so first let's start with checking the critical numbers. So it's simple here. You just take the derivative of this function. So that's gonna be 3x squared plus 10x plus 8. And then you can factor this simply 3x plus 4 times x plus 2. 6 plus 4 is 10. And then so you get -4/3, -2, right? And then you need to check if which ones of these fall into the interval. So you have to cross this out. And so what you get is sorry, don't cross this out. This is within the interval. So these are our two critical numbers here. And then you also have to check the bounds. So these are -2 and -1. So systematically, um, the bounds here are -2, f of -4/3, and then f of 1. So actually, the boundary is the same as the critical number for this case. So these are the same here. So for f of -2, that's simple substitution. That's like -14. For negative 4 over 3, it gets a bit messy, but it simplifies to negative 14.1481. And then for f of negative 1, sorry, this is negative 1 here. This should be negative 14. So your absolute minimum is at x equals negative 4 over 3, which yields to this value. And your absolute max is at x equals negative 2, negative 1. So it yields negative 14. So that's your answer. All right. So for the second problem, we're given a word problem here. Container box is to be made up from a 7 by 7 galvanized flat sheet by cutting identical squares out of four corners and turning up the sides. And we want to maximize the volume. Right, so for this, it's once again very helpful to draw a diagram. So this is a 7 by 7 sheet. So this is 7, 7. And then we have to cut out identical squares out of the four corners here. Sorry, there should be a square. And then let's label this X. So in terms of X, this entire side is 7. So this would be 7 minus 2x, 7 minus 2x, and then everything else would be 7 minus 2x, right? So the volume of the box, if you think about it, well, you can compute, you could compute it, like piecewise. Could do this, could do this, you could do this, you could do this. Then you could compute like 1, 2, 3, 4, 5. Or a simple way of doing it is just to, sorry, that's the surface area. So actually you can't do that. What you should do is like just imagine it as like a volume. So if you imagine turning up this side, what you'll get is a square of length 7 minus 2x, and then your height here is just x, right? So your box is gonna look like, so essentially it's gonna look like this. So this is gonna be 7 minus 2x. This is gonna be x, right? This is also gonna be 7 minus 2x. So if you just like turn the sides up. So essentially your volume here is 7 minus 2x squared times x, which you need to maximize. So before we dive into it, we do have some constraints here on x, right? So for x, it cannot be more than like half the length of the square. Because if you imagine your x is bounded, like you can't go this big. Um, your squares can't be this big. They have to be at most like they have to cut off at the edges here. So essentially, your x has to be less than 7 over 2 is equal to 3.5, right? And then your x also has to be like at least 0 and then 3 over 5. So now that we have those constraints, we can move on to essentially differentiating this function and finding the absolute extrema for this. So v prime of x is equal to, actually, like what we should do first is we can expand, or you can go directly with chain rule. So expanding this out, you'll get 4x cubed minus 28x squared plus 49x. So if you just like square this and you multiply it by x, that's what you get. So then v prime of x here is simply equal to 12x squared minus 56x plus 49. So finding the factors here, see, just looking. Ah, here. 7, 7. So 6, 7, 2, 7. So essentially your v of x factors out to this, and then you want to set this equal to 0. So you got x equals 7 over 6 and 7 over 2. And once again, you can't have x equals 7 over 2, so you take this value here. And then once again, you don't know whether or not this is an absolute max or absolute min. So you do have to, once again, get v double prime of x. So that's going to be 24x minus 56. So v prime of 7 over 6. Um, just multiplying, that's going to be negative 56. Negative 24 times 7 over 6. So that's going to be negative 28, which is less than 0. So this means like this is a relative maximum. So that's exactly what we want. So we have our corner here, x equals 7 over 6. So what we need to do now is just simply plug this back into our original expression. Um, v equals 7 minus 2x squared times x. So v of 7 over 6 is equal to 7 minus 7 over 3 squared times 7 over 6. So that's 14 over 3 squared times 7 over 6. Then if you simplify it, that's 686 over 27 cubic inches. Right. All right, so moving on to problem 3. Christian, who owns a store, sells 500 X phones a week for $450 each. If we decrease the price by $5, we'll get an additional sale of 10 per week. So we need to find the maximum revenue for here. All right, so essentially, like, to maximize revenue, that's simply like unit price times units sold, right? So for the unit price here, we are looking into like how much we can decrease or keep the prices. So our revenue is going to be 450 minus 5x. And then we are only considering decreasing. We don't want to increase our prices here. So this will increase our sale of an additional x 5 an extra 10 phones per week. So we are currently selling 500. So this would mean that we sell a total of 500 plus 10 x units. And then some potential constraints here, right? We are looking into decreasing, so x must be at least 0, and then it can't go beyond 450. So we can't drive our prices to the ground that much. So our x is maximum of 90, because 5 times 90 is 450. All right, so what we should do here, this is our revenue function. So to get r prime of x, that's simply just a product rule. So that's going to be 450 minus 5x times the derivative of the second, which is 10, plus negative 5 times 500 plus 10. And then simplifying, just collecting everything. That's negative 100x plus 2000. And so you want to evaluate this, so you want to set this equal to 0. So your critical number here is x equals 20. So this is our critical value within 0 and 90. but we do also have to check the endpoints. So um so don't forget to check the endpoints as well. So check 0, 20, and 90. So for R0, that's basically 450 times 500, which is 225,000. Then your R of 20 would be 350 times 700, which is 245,000. Then your R of 90, essentially like you drive your prices to the ground. So that's just 0 here. This will cross out. So that's gonna be 0. So to maximize, you essentially take this one. Take x equals 20. Then your maximum revenue. What price would result in the maximum revenue? So your maximum revenue here would be 350. So sorry, this would be your price rather. So you essentially decrease your price by a total of 100. So your price would now be 350. So this would result in your max revenue. All right. For the next problem, the position of the particle along a straight line path is defined by this, where t is in seconds. So what is the particle's instantaneous velocity? To get this, it's simply just take the derivative. So s prime of t is equal to 3t squared minus 12t minus 15 plus just minus 15. And then what you want to do here is just plug in 10, right? So that would give you 300 minus 120 minus 15. So that's 165 feet per second. Then your particle's acceleration. To get acceleration, you simply differentiate position twice, or you can differentiate velocity once. So your acceleration here would be equal to s double prime of t is equal to 6t minus 12. And then a of 10 is just 48. Oh, sorry, 48 feet per second squared. And then for the next item, what is the particle's displacement? This is really simple. It's just taking the position at 10 minus the position at 0. So to save time, let's just skip this. It's just substitution. So this 250 feet. All right. So part D is the tricky part here. Determine the particle's total distance traveled. So once again, when dealing with this, you do have to find the critical points, particularly for velocity. So find crit points for velocity, right? Because these are points where your particle switches directions, and so you want to run calculations for these regions separately. So from earlier, your first derivative, this is your velocity here. So you want to set that equal to 0. So 3t squared minus 12t minus 15 is equal to 0. So essentially what you get is just dividing both sides by 3 is equal to 0. So you got t plus 1, t minus 5 is equal to 0. So your t here is either -1, which is impossible, or 5. So essentially like it only switches at t equals 5. So to get the total distance traveled here, you simply just have to get um s of 0, s of 5, and s of 10. Because you know that from s of 0 to s of 5, you're going to be traveling in one direction only. And from s of 5 to s of 10, you're going to be traveling one direction also. So you can safely just like take values here. So substituting, you get s of 0 is 7, s of 5 is -93, and then S of 10 is 257. So you're essentially going backwards from 7 to -93, then you're going forwards here. So what you can do is simply just take the absolute value. So from 0 to 5, you travel 100 because that's 7 minus -93. And then for the other one, it is simply you basically travel 350 feet because that's 257 minus -93. So you travel a total distance of 450 feet. So let's move on to the next problem. Let's approximate the cube root of 8.1. So first, what we should do here is first define our function. So if we let f of x is equal to the cube root of x, then this is basically equal to x raised to 1 over 3. And then f prime of x would be equal to 1/3 times x raised to -2/3, which is just 1 over 3 x raised to 2/3, right? Okay. And then for this, we need to do local linear approximation. So what we should take here is we should find x sub naught such that x is close to it, right? So simple way we could do this is just set x sub naught is equal to 8. And therefore, what we're estimating here is f of 8.1, which is roughly equal to L of 8.1. It's going to be equal to f of 8 plus f prime of 8 times 0.1. So it's basically um so f of x here is just x raised to 1/3, so that's 8 raised to 1/3. And then f prime here, that's 1 over 3 times 8 raised to 2/3 times 0.1. So that's going to be equal to 2 plus 1 over x raised to 2/3 is 4. Sorry, 8 raised to 2/3 is 4, so 3 times 4 is 12 times 0.1. So that's going to be 2 plus 1 over 120, which is 241 over 120. So that's our approximation. Should be fairly close to cube root 8.1. All right, so next problem here. Suppose a cubit tank with 7-meter sides is to be coated on all sides with a special coating of thickness 5 times 10 raised to -3 meters to protect it from leakage. Use differentials to estimate the needed volume of special coating. All right. So essentially, like your differential volume here. So first we need to define your volume. This is essentially equal to x cubed. So your differential volume, which we're trying to find, is just going to be equal to 7.005 because that's the new side length of your cube, minus the original side length. So we're gonna use this. Let's just set this equal to delta v. Set this equal to delta v. Then we are gonna approximate this using dv. So to get dv, it's simple. You just differentiate the volume function to get 3x squared dx. Then for this, your x is going to be equal to 7, and your dx is going to be equal to 0.005. So plugging the values in here, you get 3 times 7 squared times 0.005, which is going to be 147 over 200 meters cubed. Right, so this is how much additional volume you'd have to get. All right, so the next problem here, An airline tango is directly above a barn while maintaining a constant horizontal velocity of 150 meters per second and a constant altitude of 1.5 kilometers from the ground. So we need to find the instantaneous rate at which the angle of elevation changes from the barn to the plane after 800 meters. Um, all right, so this is a bit, so once again, this is a bit of a tricky problem. So essentially, you have your initial position here. So this is your barn, and then this is your tango initially. And then after a while, let's say when tango's traveled 800 meters, your new position is going to be here, 800 meters. So this is going to be equal to 800 meters. And then you're going to have your angle of elevation here, essentially. And then also this one is constant at 1,500. So we are interested in uh theta here. So first order of business is simply labeling the axes, right? And so what we can do is essentially exploit trig relationships. You essentially get theta. Sorry, first of all, like what you can do here is simply check that tangent theta is equal to y over x, right? But then y is always constant at 1,500. So tangent theta is equal to 1,500 over x. So your theta is gonna be equal to the inverse tangent of 1,500 over x at any point in time. So you can differentiate this with respect to time to get 1, 1 plus, oh, sorry. You can differentiate this to get it seems like we got cut off. Anyways, let's just continue problem here. I'll just rewrite it. So this is 1,500, then this is your, and this is your y. So what you get here is that tangent theta is equal to 1,500 over x. And so theta is equal to inverse tangent of 1,500 over x. So to get d theta over dt, you have to differentiate the other side as well. So that's 1 over 1 plus 1,500 over x squared. Then you are going to differentiate this one, the via chain rule, times dx over dt, right? So what you can do is just simplify a couple values here. That's going to be negative 1,500 over x squared plus 1,500 squared dx over dt. And then so you need to evaluate at x equals 800. So your d theta here. So just plugging everything in. So that's going to be equal to negative 1,500 over 800 squared plus times dx over dt. And dx over dt is constant at, um, it should be constant at 150 meters per second to the right. So it's positive. And so for this one, this is a Pythagorean triple. So essentially this is equal to 1,700. So it's an 8, 15, 17 triangle. So what you get here is negative 1,500 over 1,700 squared times 150. Then if you simplify, that's going to be negative 45 over 578. Then this is in radians per second. So this essentially means that your theta is decreasing. So it's slowly going like this, which makes sense, right? As you go further from the height. Okay. So next we have to evaluate the following limits here. So we have limit as x approaches negative infinity of 1 minus 1 over x raised to negative 2x. So this is going to be indeterminate of the form 0 raised to infinity. So again, like the way we handle these like indeterminate forms is to bring in the natural logarithm. So that's going to be equal to limit as x approaches negative infinity of e raised to negative 2x times ln 1 minus 1 over x. So what you can do here is just check this part. So find that limit. So let's first look at this, negative 2x times ln 1 minus 1 over x, right? As x approaches negative infinity. So again, this is going to be indeterminate, but this time it's of a different form. This is infinity over 0, which is much easier to deal with. So um, what you can do here is use L'Hopital's rule. So when it's infinity times 0, it's always easier to do like 0 over 1 over infinity, which is the same thing, but then it's essentially going to be like 0 over 0. So like putting that here, what you can do here is put negative 2x underneath and then just take the reciprocal. So that's essentially what we're getting. And then if you notice, this is basically going to be a 0 over 0 form. So we can take L'Hopital's rule here. So differentiating the top, you got b. So differentiating the top, this is 1 over 1 minus 1 over x times negative x raised to negative 1. So that is 1 over x squared. If you just differentiate that. Then for this bottom side, it's going to be 1 over 2x squared. So simplifying, you basically get 1 over x squared minus x over 1 minus 2x squared. So this gives you 2x squared over x squared minus x. And then to get the limit, as this approaches negative infinity, you basically look at the leading coefficient. So this is the highest one, and then you look at the ratios. So this is 2 over 1, so that's going to give you 2. But then just to make it more explicit, the reason we arrived at that is when you have a leading coefficient here, when you have like the highest power, what you can do is divide both sides, both numerator and denominator by 1 over x squared. So this will give you 2, 1 minus 1 over x. And then you're getting as x approaches negative infinity. So this essentially gives you 2, once again, because this cancels out. But let's not forget, this is only the exponent. So the original limit is simply e squared. All right. The next one, you were tasked to find the limit as x approaches 3 over 2 from the right of 7 over ln 2x minus 2 minus 5 over 4x squared minus 9. So first thing we gotta do here is, if you notice, like you can't simply plug numbers in. So one way you could do this is to simply one way you could do this is to simply like collect the terms and then put everything under one expression. So that's going to give you 7 times 4x squared minus 9 minus 5 ln 2x minus 2. And then you're going to plug this in. And then if you notice, like, if you plug in x equals 3 over 2, this is going to cancel out, this is going to cancel out. This is going to cancel out, this is going to cancel out. So what you're left with is a 0 over 0 form. So what you need to do here is essentially differentiate the top side and the bottom side. So essentially what we're going to do is we're going to differentiate the top side here, which is going to be like 28x squared minus 63 minus 5 ln 2x minus 2. Then you're also going to differentiate the bottom side. So this is a bit like, it's a bit cancerous, but essentially what you'll end up with for the numerator, 56x. I think I'm missing, yeah. 56x minus 5 over x minus 1 over 8x times ln 2x minus 2 plus 4x squared over 9 for x minus 1. This is just product rule at the bottom, and then, yeah, product rule at the bottom. So then for this, what you can do here is just multiply by x minus 1 over x minus 1 to get 56x times x minus 1 minus 5 over 8x times x minus 1 ln 2x minus 2 plus 4x squared minus 9. And then you want to plug in 3 over 2 plus. So if you notice, like, the form is a lot neater. So what you get here, so first of all, like, 3 over 2 here, this is going to cancel out. It's going to be 0. This one is going to be a positive number. You don't have to work the exact value out. And then for this one, 4x squared minus 9, it's also going to cancel out. But then since we're approaching it from the right side, so this is like going to be, this is going to be slightly positive. So we're no longer indeterminate. So positive over something very small that's positive. So it tends to positive infinity. So that's your final answer for this limit. All right. So we do have like 2 more problems left, so we should finish on time. So let's find the absolute extrema of the function f of x equals ln sine x plus cosine x on the interval pi over 6 uh and pi over 3, like, inclusive. So it's easy to check that it's going to be continuous on this interval. So continuous on this interval. And then what you can do next is basically get the first derivative. So that's going to give you f prime of x is equal to cosine of x minus sine of x. So that's the inner differential. And then that's the denominator is going to be sine of x plus cosine of x. Then you need this to be equal to 0. And so, like, the only way this is possible on this interval is if x equals pi over 4. But then you also have to check. But then you also have to check if you also have to check if this is an absolute maximum or if this is a local maximum or local minimum rather. So simplifying, what you'll get here is equal to negative sine of x minus cosine of x over cosine of x minus sine of x. And then, so what you can do here, this simplifies to negative 2, 1 plus 2 sine x cosine x. So if you check pi over 4, it's going to be equal to negative 1, which is less than 0. So this is going to be a relative maximum. So it must also be an absolute maximum because it's the only local extremum. So then what you need to check here, is basically the like the endpoints. So on the left side, we have pi over 6. So as we approach x is equal to pi over 6 from the right. So that basically gives you ln, just plugging values in here. Sine pi over 6 is 1/2. Cosine pi over 6 is square root of 3 over 2. And then for pi over 3, can simply take the function at that point. Sine pi over 3 is going to be square root of 3 over 2. Then cosine is going to be 1/2. So it's also going to be 1 plus root 3 over 2. So essentially what you get here is that your absolute minimum is at x equals pi over 3. And your absolute max is at x equals pi over 4. All right, so we're basically done. We do have like one last problem, so we can go over it really quickly. So we have the cost and price demand function, and if 20 units are currently being produced, approximate the additional profit earned by producing an additional unit using the marginal profit function. So once again, the profit function here, that's your revenues minus cost. So that's going to be x times small p of x minus capital. And then simplifying, that basically gives you 3 over 4 x squared plus 15x minus 20. Minus 200 rather. So the marginal profit function is going to be equal to 3 over 2x plus 15. And so to approximate the 21st unit, so you can essentially like use p of 21 minus p of 20. So that's roughly going to be equal to p prime of 20. So plugging this in, it's simply going to be 3 over 2 times 20 plus 15. So that's going to be 45 pesos. All right. So you've gone through 2 samplexes tonight, and it seems that we're just about right on time. So thank you guys for attending the review session. I hope you guys are more prepared now. And please don't forget to like answer the feedback forms as well.